Starting from this week, we're going to talk about reinforcement learning. So today is pretty much basics about reinforcement learning. And then next week, we are going to talk about reinforcement learning applied to large language models, especially in training some of these models with long chain of thought. So but today is mostly on, we're going to use probably robotics as the target applications, because I think it's the easiest to think of understand reinforcement learning in those kind of contexts, the basics, because otherwise you have to deal with two things together, right? One is the reinforcement learning setting, and the other one is how do you apply it to large language models. So today we're going to make it clean, just a relatively simple kind of like robotics or sequential decision-making scenario, and we're going to introduce this algorithm called policy gradient, which is one of the core algorithm for both the robotics case and the large language model case. So so reinforcement learning. Okay, the marker is great. So the main concept here is that, so this is a technique in some sense, right? It's an algorithmic technique. The question we are trying to solve here is the so-called sequential decision making. So let's unpack this. First of all, decision making, as the name suggests, it means that you are making decisions that can affect future, that have ramifications in the future, right? So it's not like you just predict something and that's it. You make some decisions and then it will have some, affect the world. It's kind of like an action, but not just only a prediction. So it's kind of like you operate the robot, or maybe you make an Amazon order, so on and so forth. And sequential means that it's not just only one round. It's not like you make a decision and then it's done. You evaluate the decision. Actual decision will be done in a sequential way. For example, when you operate the robot, you have to give it instructions at every time step. You say like you go left, go right, and then raise the arm, so on and so forth. So in some sense, both of these combined make it complicated, because greedy algorithm wouldn't work, right? What is the optimal for the moment may not be optimal for the future. And you have to think about the downstream consequence or the ramification. And another thing that we don't discuss that much is that it also, when you are making decision, you also have to balance the return versus risk. So for example, some of the decisions you made may not be the optimal for the moment, but it's actually collecting information to some degree. For example, suppose you are thinking about, you go to a new city and you want to explore the restaurants there, right? So some of the restaurants you go just for exploration. Not necessarily is necessarily the optimal given the current information, but it's in some sense collecting information so that in the future you can make better decisions. You can decide to go to this restaurant more times or not going at all, right? So the risk versus return trade-off, or and in the technical term, it's called exploitation versus exploration trade-off, right? Exploration has the benefit that maybe in the future you understand the world better and then you can exploit much better. And exploitation is more like a more myopic thing, which is like you given the current amount of information, you just try to do the best thing right, in some sense. So this is kind of like exploration trade-off. Actually, the reason why I'm mentioning at the very beginning is because we are not going to discuss it too much in most of the cases, because in some of the applications we are seeing right now, this kind of trade-off, how do you trade off the exploration versus exploitation, is very subtle, and in many cases you just don't do it. You just don't do much exploration. Naturally, the algorithm has some degree of exploration, and that's enough. So only for some of the more classic settings, the exploitation versus exploration trade-off is well understood. So that's why we don't discuss that much. We only mostly focus on the sequential part where you have to deal with the long-term ramification. And so that's one aspect of reinforcement learning. And another aspect of reinforcement learning is that most of the reinforcement learning you are dealing with almost no supervision. Of course, there are different setups, different variants of setups, but the most classical setup for reinforcement learning and also for sequential decision making is that you don't have supervision. At least you don't have like the same type of supervision in the classification or like in the supervised learning setting. So what you only have is that you only have so for example, in many cases, you don't have the optimal actions. You don't know what is the optimal actions, even in your training data set. And you rely on the so-called reward. So we are learning from reward as opposed to labels. And I will define what reward means. Reward is often a scalar that just tells you whether the sequence of actions is good or bad. It doesn't tell you which is the good option. It doesn't tell you the optimal action. It only evaluates whether actions you output is good or not. So, and as a result, I guess maybe here I should say no human supervision, or maybe no or little human supervision. And as a result of this, another feature of it is that in most of these reinforcement learning algorithms, you need to collect data yourself in an active way, right? So, like in some sense, for example, think about how to learn the robot. You let the robots, you generate some actions for the robot, and you let the robots try it out in the real world. And if it doesn't work, then you say, oh, the reward is bad. You shouldn't do it anymore. Then you penalize it. And then if it's doing well, it happens to do well, then you say, oh, this is a good action. Then keep doing this in the future. So in some sense, it's kind of like a trial and error approach. You try some trajectories or you try some actions, and then you have a mechanism to reinforce the good actions and penalize the bad actions. So that's the general framework. So there's this data collection and training loop. You collect some data and you find out the good data, and then you reinforce by training on the good data. So that's some of the features, high-level features. Of course, there are many different details, depending on the setting, so on and so forth. But most of the cases, you should see all of these dimensions. Okay, so and next I'm going to discuss the basic modeling framework for applying reinforcement learning. And it's called the Markov decision process. In some sense, you have to have a way to describe the world and how to interact with the world to even talk about these algorithms, right? So like it's not as simple as just making a prediction. You are making some decisions. You have to model how do the decisions affect the environment and affect you in the future. So, and the modeling is called Markov decision process, which is actually a very powerful framework. So it's called MDP. So I think we're going to use probably a random example like this, something like you are navigating a robot on a 1D tip. It's a kind of like a pretty trivial task. Let's say suppose you have a 1D tip, you have like some cells, 1 to 10, and you have a robot. Let's say you have a robot somewhere on one of the cells, and you want to navigate the robot to the left or to the right, and maybe there's a goal you want to achieve. So you want to navigate the robots to achieve the goal, something like that. So I'm going to use this as a random example to map the abstract notations into the real world. You can also think of this as, for example, you have Go, you are playing Go, and you have a board which is going to be 2D, and then every action is kind of like making some moves, and so on and so forth. So anyway, and the basic kind of like I realized I have to raise it now. I hope I don't have to do this once. Okay, so the basic framework is the following. So you have one thing called capital S, which is the set of states. So states are pretty much everything you need to describe the world, right? So in this case, the state is pretty much where the robot is at right now, right? So your state set, the set of states is very simple. In some sense, it's just, in this case, in the example, it's just the 1 to, say, 10, something like this. And if you are thinking about a real robot, then the state will be something like all the positions of the arms, all the angles, the locations, or like the relative kind of like joint locations, so on and so forth, right? So it's going to be a much more complicated state. And sometimes the state also includes like a visual state, right? For example, a robot may have a camera, and that's also part of the state as well for the robot. So, and if you're playing Go, then it's kind of like the whole configuration of the board is the state. And S is the set of all possible states, right? So in some sense, this is the set of all possible configurations of the robot, or set of all configurations on the board, which is, for Go, is like 3 to the power of 361.
For the robot example, would the state include information also external to the robot, so they can do stuff about the environment?
So I think there is it's a choice, right? So you could include some of those as the states, depending on whether you think you want to model them. So in some sense, this is a modeling choice. Of course, in theory, the states should involve everything, but you cannot model every little details about everything, right? So you have to abstract away something. So I think generally speaking, people don't have, for example, whether the 3D map of the world is part of the state. Generally, no. I think it's too much, right? So you mostly just use the image, the camera images to capture some of those. Okay, so, and then there's a set of actions. So A is the set of actions. And in my toy example, I'm going to define the set of actions to be just you try to move it left or you try to move it right, something like that, right? So maybe just you have some kind of like a control, and which is like going left or going right. So, and for the real robots, the set of actions could be what kind of like how much force you apply on each of the joints, so on and so forth, right? And for Go is kind of like which location you put you make a move at, right? So, so that's the set of actions. And now the third concept is so-called transition dynamics. And what does that mean is that this is describing what will happen if you take an action on a state S. So basically, the transition dynamics is asking, if you give me a state S in capital S, and you apply an action A in capital A, so what will happen next? Right? So which state I'm going to move to? So and it's a probability distribution. So this is actually, so the typical way people do this is that this is the state, the concrete state you are at. This is the concrete action you apply, and this is a probabilistic distribution over the next state, the set of possible states, right? So this is describing what is the chance you arrive at each of the state. So in some sense, P as Z, P as A Z, this is the chance to arrive. This is the chance to arrive at Z after taking action A on the state S. So it's a probability distribution over the entire state space, right? So P as A, this is actual vector, right? In dimension, the S, right, the cardinality of S. So, of course, in many cases, PSA can be deterministic. You exactly know which is the next state you're going to arrive at. So in those cases, PSA can just output exactly the S prime, the next state you want. But in many other cases, it's stochastic. Then it's the distribution. So, so for example, in this case, you can imagine, for example, suppose your controller is not very accurate, right? So there's some kind of like errors in your controller. When you say, I'm going left, with some chance it's going left, and with some other chance it's actually going right. So then you can, in this kind of example, then you can say, oh, maybe I can say, given, let's say the P, let's say 7L, given I'm at state 7, I'm at the cell 7, I'm instructing to go left, what is the chance to go to the next, go to 6? Let's say, suppose this is 7, and you instruct it to go left. What is the chance to go to 6? You say the chance to go to 6 is probably 0.9, because I'm instructing it to go to left. but there's also a chance that it stays at 7. Let's say you also have a chance that P7L7 is 0.1. And these two sum up to 1, and all the other states have 0 mass because you cannot go to any other states, let's say. And this is just an example. I'm just, you could, but you have to define this for every possible S and A and the next state S prime. So you can say, oh, maybe PSL8 is 0 because if I tell you to go to left, you probably shouldn't go right, right? And PS7L, say 5 should be 0 as well because it's very hard to jump to two cells, right? And all the other states, all the other kind of like argument here will result in 0. And then you define this for every possible S, A, and S prime, or Z, I guess I'm using Z here. Maybe I should use S prime just to be more consistent. Sorry. For every S, A, S prime, you have a probability number, and you normalize, and you have to make sure the sum of this is 1 for each of the fixed S and A. So that's how you, so basically the constraint is that the sum over all the S prime in the possible next state, PSA S prime is equal to 1. This is a probability distribution. Okay, so this is and then you describe the dynamics. So after you have these three things, you can describe the game, right? It's kind of like a sequential decision, how you interact. The way to interact is very intuitive. So you have S0, let's say this is the initial state. Here this is indexing time, initial state. And then the algorithm or the agent, at these days people call it agent. So chooses action, say action. Let's say A0 from the set of states. And then there is an environment step, meaning that you are interacting with the environment. Your action is kind of like making an effect. So, and that means you are sampling from this distribution PS0A0 because recall that this is the distribution of the next state given the action A0 on the state S0. So you sample one state from that distribution. It's a stochastic step. And then you get S1. And then the next time the algorithm will choose action A1. Most likely from the observation S1. We're going to talk about how the algorithm chooses the action A1. But the algorithm chooses the action A1, in some way. And then you do the environment step again. So S2 is from PS1A1. And then you just loop over this. So each time you're making a decision on the actions, and then you transition to a new state. Okay, so that describes how the world is changing over time based on our decision. And then the next concept is the reward. Recall that this is actually how we learn this thing, right? So it's also how we define success, right? Because so far we are just talking about how do we interact with the world, but we also have to define what does it mean by successfully achieving some goal, right? So the reward is a function. This is a function that maps the set of states to real number. And often it's non-negative, real number, but you can also have negative reward. So, often this is kind of like something close to probably -1 to 1, something like that. And this reward just really means that how good is this state is, right? So you see, like this is a function, so this is a function of the state, right? So it's describing whether the state is preferable or not. And in other cases, people have defined reward, which is a function of the state and the action. So you are saying that this pair of the state and the action is good or not. And sometimes in the extreme case, you can even define reward as a function of state, action, and the next state, so that the reward is a function of the tuple, S, A, and S prime. I think the theory almost doesn't change at all if you use this version or this version. But for simplicity, we're just going to work with this simple reward function, which is only a function of the state. And in this case, suppose you are trying to achieve some goal here. I guess I'm drawing I guess my drawing is a little bit, maybe let's say this is like a 20. And let's say this goal is like maybe let's say 9. So how do you encode the goal being 9 into a reward function? It's very simple. You just say the reward at the goal state 9 is 1, let's say. So and reaching any other state, let's say, is say minus 0.1, let's say, for any state that is not equals to 9. So suppose you define it like this, then naturally if the reward is higher, then you are reaching the state 9 that you prefer, and you are costing yourself like some negative reward if you are wandering around on other states. Right? So basically this is, if you define the reward like this, in some sense you are encouraging the robot to reach the state 9 as fast as possible and stay there, right? Because any spending time on any other states is actually costing you negative reward, which is definitely not good.
So shouldn't it be like incrementally as it gets closer to 9, like the reward gets better and better, so that like if something is really far away, it's going to be incentivized to go closer to that.
So that's possible, but I think there are two type of, there is a little bit subtlety here. First of all, this is your choice. You can define the reward any way you want, in some sense, right? So if you believe that getting close is already kind of good, like being at 8 is better than being at 7. So there are two things. One reason you do this is because you just fundamentally believe that being at 8 is better than being at 7. And being at 8 is somehow useful for you, even though it's not exactly at 9. Right? So that's one possibility. It's just from some external information, this is your preferences. Right? You can also do this, but it could also be that I only care about being at 9. I don't really care about being at any other position. But I still define my reward with a gradual, like a slope. So that could have an algorithmic effect. So in the sense that if you define a reward like that, then maybe the algorithm is learning more easily because you have more gradient, so on and so forth, right? So that's kind of like a definition of reward is called reward shaping. So basically you care about some very discrete, fundamentally just only one thing, but actually you change your reward a little bit to make it smoother in some sense. So these are two different ways to define different rewards, right? But fundamentally this is your option, like whatever you want to do is fine. And the reward shaping stuff, so sometimes has unexpected downside. For example, suppose there's because you never know, suppose, in this case it's very clear, but what if you have a kind of like a teleporting tunnel from state 2 to state 9, right? And which you didn't know, like when you define a reward. So then you say, getting closer to 9 is better, but actually the best option might be just going to 2 and then somehow do something crazy to teleport to 9 in some way, right? So and this is more like, here it's kind of crazy, but it's more likely in the robotics case, right? For example, if you want to reach some object, right, you may naturally think, okay, the closer I am, the better, right? So basically I have reward 0.9 here and 0.8 here and 0.7 here. But what if there's something blocking here, and you have to go around, right? And then your reward function is not actually meaningful, right? In some sense, you are doing some damage to, right? You are misguiding the robot, right? So you should just really care about the final outcome.
So when defining the reward, we should expect not to really value as like this end state and the initial state and the environment is unknown, like the designer of the reward function.
Sometimes right?
Okay.
Yeah. So when you know, then you probably can do the reward shaping more effectively. If you don't know or you have little understanding, sometimes you know, but you cannot understand it. Right? It's too complex or so on and so forth. Right? Then maybe it's better to just focus on the core requests. Ask. In some sense, it's kind of like suppose you have a manager who manages a team, and if the manager knows exactly what to do, then you probably give very fine-grained reward functions. But some managers just be very hands-off and say, this is my final goal, whatever how you achieve it, I don't care, right?
Is there a notion of agents changing their reward functions?
No, not here. Yeah. I think generally not very. Yeah. So the agent is the reward is actually the overarching incentive mechanism for the agent. I don't think you can change that. In most of cases, yeah. Okay, sounds good. So okay, but this is only a reward for one state. Actually, we haven't defined the reward or the reward or return or payoff for the whole trajectory. So what happens is that you have a sequence of steps, right? So you start with S0 as we discussed, right? And you generate action A0, and then you reach a step action S1, and you you generate another action A1, and you do this, so on and so forth, right? So typically the reward for the whole thing, I think this whole thing is often called a trajectory, and in the old days it's often called episode. In the more standard RL settings, but I think trajectory seems to be a more common word. So for this whole trajectory, you can define a payoff or reward function or return. I think often people call it return or payoff by just summing up the reward at every state. And you can also talk about expected payoff or expected return by taking the expectation over the randomness of the states, right? Because the states are not deterministic. Even you give me all the exact action A1 after AT, it's still not clear exactly which state I'm going to transition to. So that's why you take expectation over it. And there's another thing which often people do is that they also introduce the so-called discount factor. Which means that you add, maybe I'll just directly modify this return. So you say you add a gamma here, and then this is gamma to the power t. For the tth term, you add gamma to the power t, where gamma is a number between 0 and 1, and it's often very close to 1. So gamma is something like maybe 0.99 or something like that. So this is in some sense a little bit more, I think the easiest way to think about it is that it's a little bit kind of like an interest rate kind of stuff, right? You are discounting the reward you get in the future. If it's too far away from the future, then it's less valuable than the reward near term, right? So if the same one, if you earn the same $1 today versus like 100 years later, then $1 today is worth a little bit more, right? So this doesn't mean that you are myopic, right? You only focus on today, but I'm just saying if you can exchange when you get the reward, then you should do it early. But sometimes you just the optimal action is that you don't get any reward at the beginning because otherwise you don't get enough reward in the future. So anyway, and once you do this, you also have the benefit that this with the discount factor. Another small benefit is that the payoff is bounded for any t, for any number of steps. Here I didn't really specify how many steps you have, right? I'm indicating that you actually can run it forever, right? So even you run it forever, so you know that if each of the individual reward, let's say, is bounded by, say, some constraint m, then the total payoff is bounded by m over 1 minus gamma in absolute value. So this is just because if you take the sum of all of this, so this is just a very simple math, which is like 1 plus gamma. Say the first time you get at most m, the second time you get at most gamma times m, and then gamma squared times m, all of this, right? This whole thing is less than m over 1 minus gamma. So this way you can more effectively talk about infinite number of steps, which is not that common anymore. But if you want to do this, some of this in some of the settings, you do care about steps being a variable that can be possibly infinite. And also, as you can see, like the discount factor encourages you to get the reward earlier, which is sometimes useful, right? For example, if you want to reach this cup here, you do probably want the robots to find the shortest path to reach the cup, as opposed to spending like a year to reach the cup, right? Something like that. Anyway, so these are just some variants here. So once you have all of this, you got a so-called MDP. So the MDP is pretty much a a tuple of all of this: the state set, the action set, the transition dynamics, the reward function, and the discount factor. So this describes the MDP. Okay, so.
Quick question about the transition dynamics. The transition dynamics is basically just like a set of rules that we can do some action on those states. So different states might have different forms of action.
Yes.
So that just constitutes like a set of rules, like which actions can be at each state.
Yes.
Yes.
Yeah. I guess I wouldn't use the word rules, but I think I understand what you mean. Like, it's a probabilistic distribution, right? Probabilistic distribution.
Right. In a real world setting, we wouldn't actually know this state. So it feels to me like how we define it as an PSA. Like, for example, if we're, I don't know, like drones learning to fly or something, like how do we define like something that's so like, there's so many things you could do, like it feels like it's intractable.
Not really, right? So I don't think, in theory, yes, but at least for drones, it's actually very easy. The state space is probably just, maybe you just need depending on what depending on what environment you're flying in, so you can just say the height, like how far, some of the velocities, maybe like whether the motor is on, it may be just actually pretty easy.
So like, for example, the height, that goes to like infinity, right? So like, how do you define a state for every single one of those heights?
No, but you have continuous states, right? So like this set doesn't have to be discrete, right? So like it's just a scalar. In your state space, there's one dimension which is a scalar, which is the height. And even you discretize, it doesn't have to be finite, right? The state space doesn't have to be finite. And after you have this MDP, the goal is just to maximize the payoff, maximize the expected payoff. So which is defined here. So the expected return. So, and how do you maximize the expected payoff? Right, you have to decide, the right actions, the sequence of actions to maximize the payoff. And one important thing to realize is that because of the Markov property, in the sense that, so this is Markov in the sense that every time you take an action, the transition, so where you transition to only depends on where you are at right now. It doesn't depend on history. It doesn't depend on anything else. It only depends on the state you are at, right? So if you choose action A1, the transition to S2 only depends on S1 and A1. So in some sense, you don't have to remember the history with this Markov property. And that means that the optimal action you make at this moment only, it means two things. First thing, it means that what will happen in the future will only depend on what is now and all the actions in the future, right? So if you are at some state st, then what happens at state st plus 1 doesn't depend on anything before t, right? And what happens at state st plus j only depends on what happens between this time, but nothing before. So there's no history dependency, and as a result, the optimal action at time t only depends on st, because everything happens before st is irrelevant, right? Like the past is the past, whatever, how you arrive at st doesn't really matter. As long as I'm at st, my future, I can ignore the past, and the future doesn't depend on the past anymore. So that's why the optimal action only is a function of st. So that's why you can define this notion called policy. This is a very special term, specific term in RL setting. So a policy means that a mapping from st to at. So, or maybe from s to t, So like I think, abstractly speaking, I'm saying like it's mapping from the set of the state to the set of action. So basically, you are saying that at is a function of st, and this function is called policy. And this is something you are looking for, right? You're looking for what is the right policy for me to get the next AT. So that's actually the only thing you care about, when you try to achieve this goal. So basically, to achieve this goal, you just have to understand what is the optimal action as a function of the state. So, and this is called policy. So, for example, in this example, if there's no this kind of teleporting tunnel, then the optimal action probably just be that if you're on the left-hand side of the goal state, you just try to go right. Otherwise, you go left, right? So that's kind of like the policy you should follow. And another, so this is a deterministic policy. Deterministic policy. In a sense that, for a fixed ST, you only output is a deterministic function, right? Given a state, you output a single action. It's known that there's always a deterministic optimal policy. And the reason is actually very simple. It's just because, you take the optimal one. If there is a tie, then you just pick any of them, right? You make it deterministic, and that's the optimal policy. So there's no reason to randomize because there's always one option that is better than all the others, or as good as all the others. So the optimal policy is deterministic, or at least there exists one deterministic policy that is optimal. However, in practice, people also talk about randomized policies. So randomized policy just means that given a state S, and often the notation is like this. The often the notation is pi of A given S. So basically, it's saying that given a state S, I need to generate distribution of actions. So a randomized policy in most cases is actually not as good as a deterministic one, but there is often in the training you need to have some continuity in some sense. You need to model this, this randomized policy with some kind of neural networks with kind of like some sampling procedures. So randomization is actually somewhat useful in the training process.
Why is randomized not as good?
Because let's say suppose you pick action. Suppose your randomized policy is that you pick action 1 with probability 0.9 and pick action 2 with probability 0.1, let's say. Right? That's your distribution of the actions, right? Action 1, 0.9 probability, action 2, 0.1 probability. And in this case, you can kind of prove that at least one of the action 1 or action 2 will be at least as good as your randomized policy. So either action 1 or action 2. And so in some sense, there's no risk, there's no point of hedging in some sense. Does it make sense? You're in between the two options, yes, yeah. It's kind of like, let's say suppose action is 1, this give you payoff maybe 1.0. And action 2 give you a payoff maybe 2.0. Then you should just, and if you're hedging between this, you are getting some reward between 1.0 and 2.0, right? But what you should have done is just taking action 2, exactly, right? You don't have to think about action 1. For training, you do want to have some kind of stochasticity. There are so many reasons. So I think it depends on exactly which settings you want to use. But generally speaking, you want some. I think the fundamental thing is you want some kind of continuity in some sense, because if it's really deterministic, often the case is that you have a hard switch between action 1 and action 2. It's not continuous, right? For some parameter, you are choosing action 1, and then suddenly you have to jump to action 2 if you update the parameter, right? Or you have to figure out how to jump to another action. So, but if it's kind of a probability distribution, then you have a continuous spectrum, right? So, say for example, at this moment you are at 50-50, and then next time you update your parameter and you move to 40-60, and next time you move to 30-70. So it's a more smooth dynamics. And in some other cases, it's just the policy have to be stochastic for some other reason, which we'll get into later. Yeah. Cool. So let's see how. Let me have a time check. Okay. So now another important concept before we talk about the algorithm. So let me think about this. How much time I have? Okay, so I think the next concept is called the so-called value function. So the value function is, in some sense, very similar to the return we talk about, but the value function is a function of the policy. So you can define the value function of a policy at state S as the expected total payoff starting from state S. So in some sense, it's not very different from the return, the total payoff. It's just you are specifying where you are starting with, and also which policy you are applying. So basically, this means that if you start with state S, you'll keep applying policy pi. What's your expected return, right? So mathematically, you just write this as the expected return conditioned on the initial state is equals to S. And also, the randomness, how do you draw this random variable? The S1 is drawn from PS0A0, and the action AT is drawn from policy pi. So that's why this is superscript pi here. So I'm describing what is the expected return for this policy starting from the state S. It's just a definition. And then you can also say you can define the so-called V star of S. So this doesn't depend on policy. This is just the max over all the possible policy V pass. So basically, you're asking, what is the best policy so that I can get the maximum return. So in some sense, this is the goal that you are trying to solve, right? So you are trying to find a policy such that you maximize the return. And the return will be a function of your initial state, because if your initial state is S, you may have higher return than a different initial states. So, but I'm getting the, so basically V star is that if I'm optimal in my future decisions, how much return I can get from state S. And the policy pi star is just the argmax of this. This is the so-called optimal policy. Right, so basically, the optimizer of this is the optimal policy, because that means it's pretty much just tautology, it's just the definition, right? You are defining the optimal policy as the one that is maximizing your future return from this status. Okay, so those are some notations. I think let me try to introduce one important concept, which is not that useful for the rest of the lecture, but I think you probably should know this at least once. I should know the existence of it and some of the general ideas. So one of the very important concepts in reinforcement learning, not that important for using reinforcement learning in large language models, but very important in the more classical sense, is the so-called Bellman equation. And the fundamental idea here is that you can write down some recursions to reason about this whole world, because the whole thing is kind of like a recursive, like it's kind of like a sequential, and you have this time thing. It's kind of very complex to think about, but in some sense you can use these techniques to get rid of the sequential aspect in some sense by solving a recursion. So I think fundamentally the technique is very similar to how do you compute these kind of things. Suppose you have a sequence, you have an infinite sum like this: 1 plus gamma squared plus gamma cube up to gamma to the t, so on and so forth. So how do you compute this? So of course you can look up the book and see a formula for this. But actually one of the simple way to compute this value is the following. you create a recursion. You say, you call this number v, let's say. Actually, I'm using the same number because it's actually kind of the same concept. And then you try to do the following. You say v is equal to this, right? But I can rewrite this equation as I take out the first term 1, and then for the rest of the term, they're all multiples of gamma. And I take out that gamma in front. So I get gamma times, because I remove one of the gamma, so then this gamma becomes 1, and then you have gamma squared. Right? So this is the equality. And then you can see this part is the same as v. It has the same form as v, exactly, right? So it's just equal to v. So then you get the so-called recursion, which means that you have a formula for v where on the right-hand side also v is involved. So it's actually, right, I think that's fundamental what a recursion means. So this is not telling you what v is exactly. On the left-hand side you have v, but on the right-hand side you also have v. But another thing is that once you have this, you can solve it. You can solve the equation. You solve it by saying you move it to the left. You say v times 1 minus gamma is 1, and then this implies v is equals to 1 minus gamma. So, and you can apply, and fundamentally the Bellman equation is just exactly the same idea with more complex settings we are dealing with. So let me give you one. So let's derive the Bellman equation for v pi. So how do we compute v pi? Let's try to apply the same idea. So v pi is what? V pi is equals to this thing, right? So maybe let me just, for the sake of kind of like clarity, let's rewrite it. Let's copy it again. So and here the I guess the implicitly the actions are drawn from the pi as we discussed here, right? So so then you try to take out the first term like that. You say the first term is S0, which is actually deterministic because S0 is equal to S. So actually the first term is Vs. And then you look at the rest of the terms. There's a gamma here as well. And maybe the t's term is RT to the RST. And you have many, many other terms, let's say. Let's say you have infinite number of terms, which makes these things a little bit simpler. And then I take the first term, and then I have the rest of them, and I remove the gamma. So I have gamma times expectation RS1 plus blah, 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 right? Times R t to the gamma to the t minus 1 times RST given what? Given S0 is equal to S. But the S0 is equal to S. Okay, so, and you see this one is really just the total expected payoff if you start with S1. The only thing is that S1 is a little bit non-deterministic here. You don't even know exactly, S1 is a random variable. You are not 100% sure which one S1 is, but if you know what S1 is, then this is just the expected payoff in the future of S1, which is kind of like a V pi S1, something like that. So the only thing we have to deal with is what is S1, right? So we just try to enumerate all the possibilities of S1. So this is RS plus, so you look at all the gamma, which is this one, and then you try to expand this. So you say this is actually equals to, you look at all the possibility of S1. What is the chance of seeing S1? The chance of seeing S1 is PS A0 S1, right? This is the chance of seeing S1 starting from state S and taking action A0. And A0 is what? A0 is my policy. What is A0? A0 is, I'm sampling from the policy pi. So A0 is really just pi S, which is A0 as well. So I'm using a deterministic policy to make it simpler. So I have the probability of seeing S1, and then I multiply the return, right? So this is the expectation of the future returns RS1 given S1, right? So you condition S1, and all the futures are still somewhat stochastic, but those are conditional S1. So then this part is the expected payoff from S1. And it has a similar, it's similar to this thing, right? It's exactly the same thing, but just starting from different initial state. So basically this is just the RS plus gamma times V pi S1. So that's my equation. So I express on the left-hand side, I have V pi S, and on the right-hand side, I still I have an equation, but the equation on the right-hand side, there's still V pi S. And here actually it's not only just one S, right? Every S actually shows up here, right? Because it's a sum over all possible S1. It's just a different of this is weighted differently.
RS0 to outside RS, should it just be like some constant, like the RS term on the left?
This is the second step.
Oh yeah, the second step, the first term, the RS step.
This one.
So this is just a constant, right?
This is just constant, yes, exactly. Okay. Because S0 is fixed with S, right? Exactly.
Call this RS0.
No, I think I should call it RS because S is the deterministic variable, is a number. S0 is kind of like a random variable.
Oh.
Right, so that's why I'm conditioning S0, the random variable, taking a value S.
Oh, I see.
Make sense? So let's examine the equations. Let's see what we got, right? So why we're getting a recursion, right? There is a recursion because on the left-hand side you have V pi. You're trying to describe V pi, and on the right-hand side you still have V pi. And also this recursion is a linear system of equations, because in some sense, like for every option of S, you have it's described as a linear combination of the V pi S for other value of S. So basically, if you list for each of the S, you have an equation like this. So and you have a system of equations, and every equation is linear in all the values of V pi S. Right. So in some sense, it's kind of like if you really brute force, let's say, this is a kind of equation where like, say V pi 0 is equals to some constant, right, which is the R0 plus a linear combination of all the V pi 0 up to V pi, say, S. And V pi 1 is the same thing, another linear combination. And every of this is a linear combination of the, right? Of course, the linear combination coefficients are different because these coefficients are different. But eventually you get a set of equations like this. They're all linear functions of this set of variables, right? Eventually you have so many variables, right? So, and then you can solve the linear system equation by just a linear solver. You can get all these V pi's. Yeah, so in this case, S is fine as discrete, yes. But the equation itself works for infinite. Like this equation in this form is true for any infinite number of S is still true. It's just like if you have infinite S, then all continuous S, you just have so many equations, right? Like, yeah, so it becomes like a functional, linear functional equation, something like that. Yeah.
So one quick question, I'm just trying to get an intuition for this. V pi S with the n, that would just represent the value function for the PCA at the end, or we just exclude the entire state space in the.
Sorry, can you ask the question again? Maybe I.
The V pi of S term at the end, like the last term in the Bellman equation, that one.
This term?
No, sorry, in the above board, the board above.
Okay, here. Okay.
Here, like the V pi S.
Yes.
This represents like this is what like the last term in my recursion. So this is just representing like the value function of like the entire state space.
No. Cardinality of S is the last state. Like I think I'm like maybe I should just use a different. Like I'm assuming like the state S is indexed by 1. Or maybe I start with 0. Then I should, yeah, like maybe okay. Let's see. So maybe let's say, suppose your state S is this. 0, 1, up to n minus 1, let's say. Okay, I think your confusion is very valid. So let's say this is n minus 1. This is n minus 1. So you have n state, they are 0, 1, up to n minus 1. So, and this last equation is that on the left-hand side, you have the n minus 1 state value function.
This is n minus, this is the size. N is the size.
N is the size, n minus 1 is the last state.
I guess the previous one also.
Yeah. It's yeah. It's, yeah. These days, some people write that way, so I'm a little bit lazy. Anyway, okay, but this is clear. Okay, sounds good. So, okay, let me think about this. So, how much time I have here? Okay, so I think I'm going to talk about use the next 20 minutes to talk about algorithm to learn the to optimize the so there are many different algorithms to find the optimal policy. So I think in the lecture notes there are quite a few. I think because this quarter we are focusing more on the large language model stuff. So I think I'm not going to discuss some of those algorithms that are not used very often for large language models. So that's why we're going to jump directly to one algorithm, which is kind of the precursor for all the other algorithms for training large language models. So it's called policy gradient, also called reinforce. And there are other algorithms in the lecture notes. If you're interested, you can read them, like in some of the sections. Okay, so okay, I think we can just start from. So what's interesting about this policy, so the algorithm we'll talk about is policy gradient. Or maybe the algorithm also have a name called reinforce with all capital letter. This is some historical reason. I think the inventor of this algorithm just named it as that. And you found that this algorithm actually doesn't really necessarily require all the backgrounds we have discussed. It's actually much simpler in some sense, to some degree, like from some dimension, right? So, and that's probably why it's easier to apply to large language model, which is kind of like have other weird features, so that you can only allow some relatively simple algorithm. So the algorithm, and also this algorithm only applies for stochastic policy. As you can see, that this algorithm just can only work for stochastic policy, not deterministic one. So here is the idea. So first of all, you need to define a stochastic policy. I'm already kind of like a stochastic policy or randomized policy. I think I already wrote it here, like which is like the way that people do it is you say pi a given s. But I also have to parameterize it because I'm going to use the neural network to parameterize my policy. So this is a pi a theta a given s. So it's the neural network that will give you this probability distribution. So and the implicit assumption here is that the probability distribution, each of the logits, each of the probability for every a and s, you can evaluate density with the neural network. The neural network will give you a density for every a and s. But you may not be able to list all the whole distribution because the whole distribution, the A can be a continuous set. So the distribution of the number of actions might be infinite, or the number of actions could be continuous, so on and so forth, right? But the minimum requirement is that this neural network will give you the density for A given S. So, and you have a way to sample from this density as well. So that's the two requirements for these algorithms to work. And then you can define this so-called return, which is basically you say you have the expected return. And here in this kind of like settings, people often talk about finite steps. And you just say I have this discounted return. And let's say I know the S0, so the S0 will come from some distribution, D0, and all the so basically, so the S come from, of course, ST come from the transition dynamics. And the policy, the action come from your policy here. So the action Okay, so that's my definition of the return of this parameter, this policy. So every policy I can evaluate the return. I'm using the letter eta as opposed to the value function here just because in this literature, people use eta more often, and there's very minor differences, which is that here your S0 is also randomized, right? Like the value function will make you fix the S in some sense. Your conditional S0 is equal to S, so that is like a function of S. But here, the initial state is also randomized. I assume I already know the initial distribution, and I'm only looking at the dependency on theta, on the parameter theta. So basically, this is what I'm trying to maximize. I'm trying to find the parameter theta such that my expected return under this policy pi theta is maximized. And my approach is actually very simple. My approach is just trying to take gradient of this eta and take gradient descent. So that's the fundamental approach. But it involves some details here. Why? The fundamental reason is that if you want to take gradient descent, think about this. Or maybe I may answer the question. Oh, sorry. This is ST. Sorry, my bad. Yeah, sorry. Yeah, you should feel, yeah. Like I was yeah. Okay, thanks. Okay, so okay, so how do you take gradient of this? If you think about it, right? So this, where does theta come from? How do you take gradient? So the theta is not even showing up in this. What's inside the expectation? Right? There's no theta. The R is known. Gamma is known. ST is your sampling of what you sampled. So in some sense, the dependency on theta comes from what is the distribution you are sampling from, but not from what's inside the expectation. So this is very different from some of the other cases where, like you have a function theta, and then you have some other things. Maybe you say, suppose you have like something like this times W, and then you take expectation over W. Right, and W is from Gaussian, I say. So this case is very different from this case because here the dependency, maybe let's even have a more general case. Let's say suppose you have, I guess suppose you have a W from Gaussian, and your function f, which is a function of theta and W, and this whole thing is a function of theta because W is averaged out. So this whole thing, let's say, is called f theta. Taking gradient of this is very easy. Because you just move suppose you have a gradient nabla here, you just move nabla inside and you are done. Right? Because this expectation is over a fixed random thing, you can just move it inside. But here you cannot do that, because if you add a nabla here, then if you move the nabla inside, this thing is actually have no gradient. There's no even dependency on theta. All the dependency come from what's in the sampling procedure. So that's pretty much the whole thing we have to deal with. So how do you take gradient when the theta come from the sampling part? So let's try to abstract this question a little bit so that we can have a more abstract view. So in some sense, the way to abstract this is that you say, in some sense, the question is this. You want to take the gradient with respect to theta, and your object is something like of this form. What's inside the expectation doesn't depend on theta, but the sampling procedure depends on theta. So in some sense, if you look at this, the mapping here is that the x will map to the sequence, the trajectory. And your f is kind of like that reward function, right? In some sense. So f is the reward function. So f of the trajectory is in some sense the sum of the reward. Okay, so that's the my abstraction. So, but I want to deal with a simpler setting first. So how do you take the gradient here? So eventually the way is, okay, so the way is like this. So you first try to make the theta dependence on theta more explicit. you say, let me try to integrate this, right? So what does this really mean? This means that expectation of this really means that I integrate the probability, multiply the probability times the value, and I integrate over x. So, and now when you write this way, then you can swap the gradient with the integration, because this integration doesn't depend on anything about theta. The integration is with respect to Lebesgue measure, or with respect to it's the very, very usual integration. So then you can just say this is integration of gradient of theta applied to p theta x fx dx. And then you say fx doesn't depend on theta. So this is really just the integration of nabla p theta x times fx times dx. And in some sense, this is kind of like an okay formula. The problem is that, you know, if this is the formula you are dealing with, how do you integrate x? Right? I don't have a way to integrate x. So it's still very inconvenient for me to compute this. You know, it's convenient for me to take the gradient because this is something I can compute, this is something I can compute, but I don't know exactly how to integrate. So eventually, what I want to do is I want to actually come back to some sampling version so that I can sample the gradient. So what do I mean by that is that you do this trick where you will write this as the gradient of theta of log of p theta and times p theta dx. So first, let's verify this is identity. And there is identity just because, very simple, like the gradient of log is just p theta x. It just equals to the gradient of p theta divided by p theta. This is by a very simple chain rule. Right? And then you multiply this p theta with this p theta, they got cancelled, you get the first one. So that's why this is identity. And why you really want this? The main reason is that you want this term to show up so that you can get back to the expectation form. So basically, if this term shows up, this is equals to the expected value of nabla theta log p theta x, and where x come from p theta. So, right. So because this p come into the expectation, right? The expectation of something is the same as the probability times the value. Yeah.
The other reason is we remove gradients of logs because eventually p theta will be a product of stuff, and then you can put out with the log. And that's what it's usually. Right?
Not really. I think even it's a product can do it. Yeah. Even it's I think even it's a product of the probability, you can still take gradient with respect to the product of the probability. I don't think that's a fundamental issue. Sorry? Oh, yeah, sorry, I'm missing it. I should follow my notes more carefully. Yeah, but I think if even you have a product probabilities, I think fundamentally there is no reason. Maybe there's some stability issues, but yeah, but I don't think that's necessarily the main reason. Yeah. Okay, so sounds good. And okay, so that's our formula for taking the gradient. So everything here can be evaluated, right? So you can evaluate this, you can evaluate this, you can sample from this. And that's how you get a gradient estimator. And note that this is the estimate for the gradient, not for the original function. So, okay, I have 5 minutes. Let's see whether I can. So the rest of the things is to apply this to the particular choice of x that we are seeing here. So if you apply this tool, then you will see the gradient of eta theta is the gradient of this guy. So it's the gradient of the expectation of the sum of the r's right? So, and then you apply this tool, you know that you can swap this in this way. So still the trajectories, right? So S0 and A0, so on and so forth, are from the theta, right? The pi theta, right? So, and here you take this part is the same as f, which you keep, and you add another term, which is the gradient. Gradient of theta of the log of the probability. So what's the log of the probability of S0 times the probability of S0? Okay, log of this times the probability of S0, A0 given S0, times the probability of S1, which is S0, A0, S1, so on and so forth. And so basically, eventually you get P of AT given ST and P ST AT ST plus 1. And then this times the sum of the reward, gamma T R ST. So that's the formula. Okay, so fundamentally, we are already kind of like almost solved the problem because you see everything here you can compute. We can still simplify it. I think we'll see whether we can simplify a little more in 4 minutes. But eventually, I think fundamentally we already achieved the goal in some sense because everything here can be computed. Okay, so, and now let's try to simplify a little bit. Okay, so actually maybe I'm not entirely correct in the sense that everything is computable here. So, so these terms may not be computable, but they don't depend on theta. So, especially if you write down more carefully, so you have this expectation, and the first one is gradient of the log of the so this is the log of a product, which is the sum of the log of each of the terms. So you have gradient of theta with respect to theta, sum of log of P, say P ST AT ST plus 1, plus the sum of the log of P AT given ST, and then this times another sum of R gamma T RST. And these terms you may now know. The transition dynamics, we at least so far we didn't assume they are known. And in this algorithm, you don't have to know them. You don't have to know the transition dynamics, but you can drop this term because their gradient with respect to theta is 0, because they don't even depend on theta. So gradient of this is 0, just is gone. And so basically you only care about the rest of them. So then you get okay, so this is much more simplified. And there is another further simplification, which is the following. So let me see whether I have time. Okay, I may have to refer to the notes. So you can see that this is the product of two sums, right? So you have many terms here. Let me see, how do I express this in 1 minute? So maybe I'll probably just stop here so that it's a little bit, I think it will take like 5 minutes so that these people will kick me out. Or maybe 5-10 minutes. So, but this is already very simplified in some sense, right? Like everything you can compute and you can just take the product.
Computable, but wouldn't it be computationally intractable for cases like LLMs where it's like if you have if you try to generate all possible output generations, then that would be
So where did you enumerate all the output generations? What do you mean by that?
Like the expectation of S0, A0, and then if you wanted to do that for like a sequence length of like T, or T is like somewhat large, then you would have like the entire vocabulary to the power of T, which is...
Oh, but you never enumerate all of them. You just sample from it. You just actually sample one trajectory sometimes. You sample 5, you 10.
Like, what would have you do the process?
There's no Monte Carlo estimation here. It's just a very simple sample. You sample from the distribution. You want to compute a random expectation for a random variable. You just sample from the random variable and then take the empirical mean. And yes, how large the variance it is, it's a little bit hard to say. I think we'll discuss next time how to reduce the variance, the size of the variance. But I don't think the variance here is kind of like crazily big. Of course, you still want to reduce it, but I don't think it's something like you say that the variance is like exponential in T or anything like that. Yeah.
It worked well enough.
Sorry?
It worked well enough in practice.
In practice, you always care about reducing the variance. Even the variance is not huge, you still want to reduce it. I think people have many ways, right? Yep. But it's not like astronomical in some sense.
Yeah.
Yep.
Like the variance of this is not so bad as it comes to that.
Exactly. Okay, thanks.